Okay, we're going to talk about now predicting the products of a chemical reaction. Some prerequisite things you need to know. These are things we learned in previous units or sometimes even in physical science in the 9th grade if you're taking chemistry in a high school in this state anyway. We need to know how to put chemical components together in compounds. Now most of the time in this section anyway, we're going to be talking about ions. One ion combining with another ion and when they do that and when they don't and how to balance those out and stuff. So we also need to know how to balance compounds, and most of the time it's going to be ionic compounds in this section we're talking about here. Okay? There are a few exceptions, but for those it's pretty much straightforward memorization, and only a few. We need to know how to classify reactions. We're going to need to learn how to classify. We learned to do that already in this unit. There are only going to be 4 of these we have to deal with in this section of this unit. But in this unit we've already learned to classify 6 kinds of reactions. And then we have to be able to balance equations. Those are things we've already learned. We're going to be applying in the process of predicting the products of chemical reactions. Okay? Now the kinds of equations for which you will be able to predict products are, and there, like I said, there are only 4 out of the 6 you've learned. You have to learn how to predict the products for single replacement reactions, double replacement reactions, acid-base double replacement reactions, and combustion. Now, if you're trying to take notes, and if you're watching this video because you were not in class and you're trying to catch up, press the pause button, take down the notes, and then move forward, okay? I'm just going to speed through these for the video here. All right, some things you need to know that are new things to know, okay? How and when to use solubility rules, and how and when to use the activity series. And these are found in the test references. So if you get out your test references, if you're in this class anyway, you'll have a set of test references with solubility rules and activity series. Okay? We need to learn how to use these solubility rules. And I'm going to guide you through this in just a little bit here. First I want to point out the activity series. There are really 2 parts to the activity series. There's an activity series of metals, but don't forget about the activity series of halogens. That's very important. It's sort of tucked in down here in the bottom, but it's very important. Some other things about the activity series you need to be aware of. In the middle of this activity series of metals is hydrogen. And hydrogen is not considered a metal, but it's important because this is the hydrogen ion from an acid. So when we have acids, these metals up here react with acids and these down below it don't. And that hydrogen ion is from the acid. Because what happens with an acid is this. When you put it in water, it is an acid because it gives away hydrogen ions. That's what an acid is. That's what makes it do its work. So the acids will react with all these metals. But we have said before that water is generally considered not to be an acid, but there are lots of exceptions. There are times when it will behave like an acid, and this is one of those times. If water is in steam form, that is to say it's been heated up, it's been boiled, it's in steam, then if you put these metals from here up, from this line right here up, if you put these in steam, the steam does behave like an acid. So these metals here react with the water as if it's an acid, and that hydrogen ion then comes off the water and reacts with these metals and leaving behind that hydroxide ion. We've talked about that before, how water dissociates, and that's how it behaves like an acid. Now, these metals from here up are so active that they will react with cold water, regular liquid water, and strip that hydrogen ion off. The water then is behaving like an acid in that it gives away a hydrogen ion to react, and these metals will displace that hydrogen ion and will join up with the hydroxide part of that water. Remember, water dissociates into hydrogen ions and hydroxide ions in the Arrhenius acid-base theory, and that's what we're dealing with at this point in time. Okay? Something else about the solubility rules before we move on. There's a soluble section and an insoluble section. So the compounds that are mentioned here, and you have to kind of figure out what they're talking about, because it doesn't give you every single compound. What it says here is that all compounds in which nitrate is part of the formula, those are all soluble. Acetates are all soluble. Ammonium compounds are soluble, and so forth. But it also has things like chlorides, bromides, and iodides, which are soluble unless they're soluble, meaning they'll dissolve in water, unless the chloride, bromide, and iodide is bonded with silver or lead or mercury 1. So there are some exceptions to them being soluble. Now, soluble means that something will dissolve. It doesn't mean that it has dissolved or it is dissolved. It means it will dissolve. So you have to put it in water to get it to dissolve. Once it does dissolve, it's aqueous. So soluble means it will dissolve. Once it has dissolved, it's aqueous. Down here we have compounds that are mostly insoluble. For the most part, they don't dissolve in water. Now, for both soluble and insoluble, there's a lot of given sort of gray areas in here. Okay, it means most of the time, for the most part, most of it will not dissolve. Most of it will dissolve. That's what these two categories mean. Soluble meaning dissolve. Insoluble means not dissolving in water. But everything will dissolve in water. Just these down here don't dissolve very much at all. So carbonates generally, compounds with carbonates generally don't dissolve. Iron carbonate is insoluble. If you put it in water, it's not going to become aqueous. It'll be a solid. It forms what's called a precipitate. Okay, it falls down to the bottom as a solid if it's in an aqueous environment, if it's dissolved in water. However, carbonates that are combined with group 1 elements, those are metals. That's in column 1. Those are the alkaline metals. Okay, sodium, potassium, sodium, potassium, lithium, rubidium. Those are all group 1 metals. If you combine those with carbonates or phosphates, then those kind of carbonate or phosphate compounds will be soluble. They will dissolve in water if there's water around, and that's a key thing, is they will dissolve if there's water around. All right. So that's what we need to know about solubility rules and the activity series, okay, in general for right now. Then we want to know about a driving force, okay? What is a driving force? A driving force is what makes a reaction occur, okay? There are lots of driving forces. We are only going to be dealing with a few in this section. If there is no driving force, there's no chemical reaction. And NR, capital N, capital R, is the symbol we use for no reaction. You can write out the word no reactions, write out the words no reaction if you want to, but you can also use the symbol capital N, capital R. Make sure they're capitalized. Okay? All right, let's talk about solubility rules then, in the sense that these will be used to help determine if a driving force exists, only if it's a double replacement reaction. So there are other things we're going to use for figuring out if there's a driving force, but solubility rules will be used as one of those helps for figuring out if there's a driving force. The activity series, on the other hand, is used to help determine if a driving force exists for a single replacement reaction. Okay, we learned to classify reactions yesterday in this class, and once we can classify them, then we can learn whether we're going to use the solubility rules or the activity series for determining if there's a driving force. One thing about solubility rules, though, you also use those when you have single replacement reactions, but they're not used to determine if there's a driving force. Solubility rules are used for determining if there's a driving force for double replacement reactions. In single replacement reactions, they're still used to see if something is going to be dissolved in water or not. All right. In a double replacement reaction, there are 3 kinds of driving forces. The formation of, that means we're making something, it's on the product side, it's on the right-hand side of the arrow in that equation. If there's a formation of a solid in a liquid environment, we're forming what's called a precipitant. Okay? You have stuff dissolved, and when you react those dissolved things together, something falls to the bottom as a solid, that's a precipitant. If you form water, HOH or H2O, that's a driving force. If you form a gas, that's a driving force. In single replacement reactions, the driving force is when a metal is more active than another metal in a compound, or a halogen that's by itself is more active than a halogen in a compound. So a metal or halogen that's by itself, that would be on the left-hand side of the reaction, on the reactant side, is more active than one it's like, a metal being like a metal and a halogen being like a nonmetal, than one in a compound. Okay? So let's see how that plays out in an equation here. Okay? So say we start with magnesium a metal, which is they're going to be a solid. Metals are all solids if they're by themselves, whether they're dissolved in water or not. They're going to be solids unless you have mercury. Mercury tends to be a liquid when it's by itself. We're going to put it in a solution. Aqueous means dissolved in water. That's zinc sulfate. Okay? So what we want to do is to figure out, will magnesium replace the zinc? And then you'll have a reaction. Well, in order for that to happen, magnesium has to be higher than zinc, where zinc is right here. So it is higher. Magnesium is more active then, and it should replace zinc in zinc sulfate. And so we get magnesium and sulfate together. Zinc then gets kicked out by itself. Zinc, being a metal, is a solid. To figure out if magnesium sulfate is aqueous or not, we use the solubility rules. Sulfates are mostly soluble. There are some exceptions. Sulfate combined with calcium, sulfate combined with strontium, or barium, or mercury, or lead to a silver. But sulfate combined with magnesium is not an exception. So magnesium sulfate will be soluble. If there's water around, it will dissolve. And here's an aqueous. It means we can dissolve it in water because there's water around. This aqueous right here tells us that. We need to make sure we balance this compound. Magnesium has a 2+ charge. You can find that here on the activity series, 2+. You can also find that on the periodic table with oxidation numbers. Sulfate has a 2- charge. If you didn't know that, well, you'd look it up on the common ions list in the test references in this class. Sulfate has a 2- charge here. So I need 1 magnesium, a 2 positive charge particle, 1 sulfate, a 2 negative charge particle. So the charges balance out. We only need 1 of each. Zinc by itself is a solid. And now we're ready to balance the equation. And what we see is when we use this atom inventory that we have the same number of atoms on both sides, so it's already balanced. We don't have to put any coefficients in here to balance this particular equation. All right, so let's review some of these things we just talked about. Because magnesium is higher on the activity series, it is more active and will replace zinc, the ion, and it's driving this reaction forward. Okay? So, if you put magnesium with sulfate and put zinc by itself, so magnesium with sulfate, zinc by itself, you must determine the correct balance for the formula of a combination of magnesium and sulfate. Magnesium is 2+, sulfate is 2-, so it's balanced with 1 magnesium and 1 sulfate. Charge balance. Have as many positive charges as negative charges. Okay? Then we're going to use the solubility rules to determine the physical state of ionic compounds, such as magnesium sulfate, when water is present. So there was water present. We can see that because this aqueous right here symbol means dissolved in water. The symbol AQ for aqueous means that you have water. Okay, water is present. So it means dissolved in water. That's what aqueous means. The presence of H2O or HOH would also tell you water's there. Okay? And finally, then we're ready to balance the equation. That's what we did. So let's look at this equation here, or this partial equation. Sodium carbonate and strontium. Sure. Okay, so pay attention. All right, so strontium is above sodium on the activity series. So there is a driving force. Strontium will kick out the sodium. And strontium then joins up with the carbonate. And that's what we have right here. Okay? Sodium then is by itself because it's been kicked out. Okay? Strontium has a 2+ charge. You can find that on the solubility rules or on the periodic table with oxidation numbers. Carbonate has a 2- charge. You find that on the common ions list. Since strontium has a 2+ charge and carbonate has a 2- charge, we have a particle with a 2+ charge and a particle with a 2- charge. That's already balanced. So we don't need any more subscripts to balance this formula. Okay, this formula is already balanced. You're going to look on the solubility rules, and you'll find that carbonate compounds are mostly insoluble. There are some exceptions, but combining carbonate with strontium is not one of the exceptions. So, strontium carbonate is insoluble. Since there's water around, we know that because of this aqueous right here. Since there's water around, this is not going to dissolve in that water. It's going to fall down to the bottom as a solid. Okay? And the metal sodium we're going to treat like a solid. Alright? Got that? Now we're ready to balance the equation. And to balance the equation, you always use an atom inventory. So here's the atom inventory. We've got 2 sodiums on the left, 1 carbon on the left. Y'all probably help if you were paying attention up here. We've got 3 oxygens on the left and 1 strontium on the left. On the right hand side, I've got only 1 sodium right now. Remember, sodium is not one of the 7 diatomic elements. So when sodium is by itself, it's just sodium, not sodium subscript 2 or 8 or 44. Just sodium. Okay? Now there are some elements that are more than diatomic, but I'll just have to tell you about those. I don't expect you to know those. Okay? Metals are not considered to be diatomic, with the exception of mercury, and don't sweat it. Okay? We'll deal with those when we deal with those. All right? If you have a metal by itself, assume it's just that metal. All right? So now we have 1 carbon over here, 3 oxygens, and 1 strontium. And so to balance the equation, we need to have 2 sodiums. Everything else is already balanced, so we need a coefficient of 2 here. Cancel that out and change it to 2, and everything is balanced. Everybody got that? All right then. Let's try something else. Let's try it. Try it. Alright, so what's the first thing you're supposed to do if you're supposed to finish this equation? Alright, you're going to look at the activity series and try and figure out if you have a driving force or not. Now this is only going to work, this process we're using right now, only we're going to work for single replacement reactions. It's a different sort of process for double replacement reactions, okay? Or combustion for that matter. Alright? So is there a driving force for this reaction? Oh, we got a bunch of no's. Alright, so we don't, you're right, there's no chlorine on this, but there is chlorine down here, but that's not what you're dealing with, and here's why. We've got a metal by itself. The metal is by itself, if it's going to displace something, it has to displace something it's like, meaning another metal. Magnesium is the other metal. In order for iron, Fe is iron, to displace magnesium, it's got to be more active. And we know it's more active if it's higher on the activity series. Problem is, iron is lower than magnesium. So iron will not displace magnesium. What does that mean? No reaction. Well, you can, but why would you do that? I just write out NR, but if you want to write out no reaction, that's okay. All right, let's try another one. All right. What does that mean? Yeah, because it has to be higher. It can't be the same. Okay, chromium is on the same horizontal row as chromium, the ion. No, because remember bromate has a 1 negative charge chromium has, this particular chromium has 2 plus charge. You can't add more chromiums to the formula. Okay? Basically, remember that metals and halogens don't replace themselves. Okay? Why would a metal replace itself? You know? It's kind of like Lincoln's famous quote, to justify a civil war, to stop the states from seceding from the Union. You know, a house divided against itself cannot stand. You know, why would chromium replace itself? Okay, it doesn't. That's the short answer. All right. So I'm going to give you. All right. Let's take a look at this worksheet.
Are you going to explain it?
Yep. Let's take a look at the worksheet. All right. What it says here at the top. Can you read?
No, I cannot.
Oh, you're in high school. You can read. Come on. Read what it says.
Predict which metal listed below is placed in each of the solutions below. What is likely to happen? Explain how you believe this will happen.
Okay. So here's the metal column. Here's the solution column, and you know it because it says so at the top of the column. That's what a column label's for. Okay? So if I put zinc, the metal, okay, in zinc nitrate, the solution, no reaction? Why is that?
Because it can't replace it.
Yes.
Fine.
Hi. All right, let's take a look at the next one. Look at the next one then. Look at your solubility rules and figure out if we're going to have a reaction or not. And whether or not it's a reaction, explain why. Huh? It is easy enough. So somebody tell me if we're going to have a reaction here. I heard somebody say no. No reaction? Really? Let's take a look at this activity series here. Okay? We've got zinc, and zinc is right here, and zinc is right here, and silver's way down here. Is zinc higher than silver?
Yep.
Zinc is by itself. Silver's in the compound. It box it out. You can call it box it out. It's going to knock it out, okay? So there is a reaction. So a reaction occurs.
Because zinc is higher than...
That's what goes here. What are we going to say?
Zinc is higher charge.
All right, now that's an indication of what is really going on. It is higher. We can put it that way. We can say zinc is higher on the activity series. Huh? It is by itself, but we're going to put it, what it says up here is we're going to put this zinc metal in a solution that contains this. Okay? It's higher on the activity series. The activity series is only arranged the way it's arranged to tell us about zinc and silver, the ion. What does it tell us about those? Okay, so essentially what it says is, therefore, zinc is more active than the silver ion. Therefore, zinc is more active than silver, the ion. Therefore, 3 dots mean therefore. Yes?
If the other thing, like on the other side, like CU, if that was higher than zinc, would it do some reaction?
Right here? Zinc has to be higher than this for a reaction to occur.
Okay, if the C is higher, there's no reaction?
There'd be no reaction, right? So if one of these things is higher than zinc, zinc is not higher, there's no reaction. All right, now, huh?
Zinc is higher.
Then what's going to happen?
There will be.
There'll be a reaction. Okay, good. Now, let's jump down to this one right here, zinc, and this thing right here. What is this thing right here? Hydrochloric acid. Very good. All right, now, so acids per se are not listed on the activity series. At least it doesn't look like it so far, maybe, but it is. I'm going to explain why acids are listed here. Okay? Any acid you put in water, according to the Arrhenius theory, breaks up into hydrogen ions and something else. So this right here is the acid. H plus. So is there a reaction here? Is zinc higher than this H plus? So there's going to be a reaction. Why? Explain it. Okay, now look, we're almost out of time, so let me tell you about your homework real quick. This is homework. Let me tell you about it. Can you please be quiet so you can leave when the bell rings? So you're going to finish this worksheet. There's a little bit more on the top. In your lab notebook, you need to also put a chart for recording your results from the lab on Friday. Like this right here. So what you're going to do today for homework is make predictions and justify them. What you're going to do in the lab is observe and then write down whether or not those observations support your prediction or refute them and why. Okay? So I've sort of squeezed. Can you please stop packing up so you can listen to me? I've got really narrow bars in here. You need to make sure there's plenty of space for your observations and justifications. Okay? Yes, the whole thing. If you need more than one page in your lab notebook, you can do that.
No, I didn't know if you wanted us to copy it or not. That's what I was asking.
Well, this whole thing here needs to be in your lab notebook, but more space than I've given it. Okay? All right. Now you can pack up. What?